Welcome to G Fun Facts Online. Today, we are going to unravel a mystery that shifts our perspective from the titans of the cosmos to the absolute runts of the galactic litter. For decades, the story of black holes has been dominated by size. When astronomers wanted to study the supermassive monsters of the universe, they looked to the sprawling spiral arms of giants like our own Milky Way, or the elliptical behemoths anchoring the centers of massive galaxy clusters. It was always assumed that these gravitational monsters were the exclusive property of the cosmic elite. But a revolution is quietly taking place in astrophysics. We are finding that the universe has a way of hiding its most colossal secrets in the smallest of places. Hidden within the faint, unassuming glows of dwarf galaxies, collections of stars often thousands of times smaller than our own, lies the key to understanding the early universe. We are discovering that these tiny galaxies are not merely passive islands of stars. Many of them harbor massive black holes that defy our previous understanding of scale and formation. These are not just anomalies, they are fossils left over from the dawn of time, frozen in a state of arrested development that allows us to peer back billions of years into the history of cosmic growth. This is the story of how we found the monsters hiding in the nursery, and why the discovery of massive black holes in dwarf galaxies is rewriting the biography of the universe. To understand why a black hole in a dwarf galaxy is so significant, we must first address the elephant in the room, or rather, the quasar in the early universe. For the last half-century, astronomers have been wrestling with a mathematical impossibility. When we point our most powerful telescopes, like the James Webb Space Telescope, toward the edge of the observable universe, we see quasars. These are brilliant beacons of light, powered by supermassive black holes, blazing away just a few hundred million years after the Big Bang. Some of these black holes are a billion times the mass of our Sun. The problem here is time. Black holes grow by eating gas and dust, a process called accretion, or by merging with other black holes. But there is a speed limit to this gluttony, known as the Eddington limit. If a black hole eats too fast, the radiation pressure from the superheated gas pushes the food away, effectively choking off the meal. Even if a black hole ate at its maximum theoretical speed from the moment of its birth, it is difficult to explain how it could reach a billion solar masses in less than a billion years if it started as a typical stellar mass black hole, which is usually only about 10 to 100 times the mass of the Sun. It is akin to finding a fully grown blue whale in a nursery school. The timing simply does not add up. This paradox led to the seed theory. Astronomers realized that these early giants must have started from seeds, but the question remained, what kind of seeds? There are two main theories. The first is light seeds. These would be the remnants of the very first stars, known as population 3 stars. They would be roughly 100 solar masses. However, if these are the seeds, the early growth of black holes must have been impossibly efficient, breaking the laws of physics we currently understand. The second theory creates a shortcut. This is the heavy seed theory. These seeds are the result of a more catastrophic event, the direct collapse of a massive cloud of pristine gas. In this scenario, a cloud collapses not into a star, but directly into a black hole, weighing 10,000 to 100,000 solar masses. If you start with a heavy seed, growing a billion solar mass giant by the time the universe is a toddler becomes mathematically possible. But here is the catch. We cannot see the seeds of the giant galaxies today. The Milky Way and Andromeda have merged and grown so much over 13 billion years that their original seeds are buried under layers of cosmic history, erased by billions of years of eating and merging. We cannot check their birth certificates. This is where dwarf galaxies enter the stage. Dwarf galaxies are the Peter Pans of the universe. They are galaxies that never grew up. Because they haven't undergone the violent mergers and chaotic growth spurts of their larger cousins, they are pristine time capsules. If the early universe was filled with heavy black hole seeds, the leftovers should still be sitting in the centers of dwarf galaxies today, untouched and hidden in plain sight. Finding them, however, was supposed to be impossible. Why did it take so long to find them? The answer lies in the deceptive nature of black holes. Contrary to popular belief, black holes do not suck. They just have gravity. Unless a black hole is actively eating, tearing apart a star, or gulping down a gas cloud, it is invisible. In massive galaxies, black holes are easier to spot because they are often active. They have huge reservoirs of gas to feed on, lighting up as active galactic nuclei. But dwarf galaxies are often gas-poor or have very quiet environments. A 100,000 solar mass black hole sitting quietly in a dwarf galaxy exerts a gravitational influence so small that it affects only the stars in its immediate vicinity, a region often too small for ground-based telescopes to resolve. For decades, the occupation fraction, the percentage of dwarf galaxies containing a black hole, was assumed to be near zero. The mantra was simple: small galaxies have no black holes. That changed with the development of high-resolution X-ray imaging and the launch of the Chandra X-ray Observatory. While optical telescopes were blind to these hidden monsters, X-rays can penetrate the dust and gas. When matter falls into a black hole, it heats up to millions of degrees, emitting X-rays. Even a snacking black hole in a dwarf galaxy might emit a faint X-ray signature. The hunt began, not by looking for the bright beacons of quasars, but by sifting through the noise for the faint whispers of mini-monsters. In recent years, a series of discoveries has shattered the silence, proving that dwarf galaxies are teeming with massive black holes. Each discovery revealed a different personality of these hidden objects. First, let us look at the creator, a galaxy known as Hennes A2-10. Located just 30 million light-years away, Hennes 2-10 is a starburst dwarf galaxy. For years, astronomers debated the source of strong radio and X-ray emissions coming from its core. Was it a supernova remnant? Or was it a black hole? In 2022, the Hubble Space Telescope settled the debate with a stunning image. It revealed a bridge of hot gas connecting the galaxy's center to a nearby stellar nursery. But this bridge wasn't destroying the nursery. It was creating it. The black hole at the center of Hennes 2-10, weighing about 1 million solar masses, was launching a jet of gas that was slamming into a cloud of dust. The impact compressed the gas, triggering a wave of star formation. This was a paradigm shift. In large galaxies, black holes are usually quenchers. Their powerful jets blow away the gas needed to make new stars, killing the galaxy. In Hennes 2-10, we saw the opposite, a black hole acting as a creative force. It suggests that in the early universe, black holes and galaxies may have helped each other grow in a symbiotic relationship. Then, there is the silent giant, Leo I. If Hennes 2-10 was a creator, Leo I was a ghost. Leo I is a dwarf spheroidal galaxy orbiting our own Milky Way, a satellite galaxy that is widely considered dead because it has very little gas and no new stars forming. Astronomers at the University of Texas at Austin were studying Leo I to measure its dark matter content. They tracked the movement of stars, expecting to find that the galaxy was held together by a halo of dark matter. Instead, the data didn't make sense unless they added a massive object at the center. The models revealed a black hole of 3 million solar masses. The shock here is in the comparison. The black hole at the center of the Milky Way, Sagittarius A star, is 4 million solar masses. Leo I is 100,000 times smaller than the Milky Way, yet its black hole is nearly the same size. This overmassive black hole defies all scaling relations. It suggests that some dwarf galaxies might be naked cores, the stripped-down remains of larger galaxies that lost their outer stars in a tussle with the Milky Way, leaving only the dense center and the monster black hole behind. Next, we have the buried treasure, MRK 462. In 2022, researchers using the Chandra X-ray Observatory looked at 8 dwarf galaxies that showed optical hints of activity. Only one, MRK 462, revealed the smoking gun, high-energy X-rays. MRK 462 hosts a black hole of about 200,000 solar masses. But crucially, this black hole is heavily obscured by dust. Optical telescopes missed it entirely because the dust blocked the visible light. Only X-rays could punch through. This discovery implies that our current census is vastly incomplete. If many dwarf black holes are buried in dust, there could be millions of them hidden in plain sight, undetectable by standard surveys. This leads us to the missing link in black hole physics: intermediate mass black holes, or IMBHs. We see stellar mass black holes, which are 10 to 100 suns, and we see supermassive black holes, which are millions to billions of suns. But the gap between 100 and 100,000 suns has been empty for decades. We found the babies and the giants, but never the teenagers. The black holes found in dwarf galaxies like MRK 462 are finally filling this gap. Why does this matter? Because IMBHs are the seeds. A 200,000 solar mass black hole in a dwarf galaxy is likely a heavy seed that never got the chance to grow up. By studying the spin, accretion rate, and chemical environment of these IMBHs, we are effectively studying the embryos of the supermassive black holes that power quasars. The recent release of data from the Dark Energy Spectroscopic Instrument, or DESI, in 2025 has exploded this field. Early data identified over 3,000 dwarf galaxies with signatures of active black holes, tripling the known number overnight. This suggests that the occupation fraction is much higher than we dared to hope. The universe is teeming with these seeds. However, not all of these black holes stay at home. In 2025, a study led by the Shanghai Astronomical Observatory identified a rogue black hole in a dwarf galaxy 230 million light-years away. It wasn't at the center. It was offset by 1,000 light-years, wandering through the galaxy's outskirts while launching radio jets. How does a black hole get lost? It usually happens through recoil or slingshot events. When two black holes merge, the emission of gravitational waves can be asymmetrical, delivering a kick that shoots the resulting black hole out of the galaxy at millions of miles per hour. Or, in a three-body interaction, the lightest black hole is often ejected into deep space. In massive galaxies, the gravity is strong enough to hold onto a kicked black hole, but in a dwarf galaxy, the gravity is weak. A merger event can easily eject the black hole entirely, leaving the galaxy barren while the rogue monster roams the intergalactic void. This may explain why some dwarf galaxies seem empty. Their hearts were ripped out eons ago. The launch of the James Webb Space Telescope has poured gasoline on this fire. James Webb allows us to look back to cosmic dawn, the era of the first galaxies. It has discovered a class of objects dubbed little red dots. These appear to be compact, red galaxies existing in the first billion years of the universe. Upon closer inspection, many of these little red dots are dominated by supermassive black holes. In November 2024, astronomers announced the discovery of LID 568, a black hole in a dwarf galaxy just 1.5 billion years after the Big Bang. It was feeding at 40 times the Eddington limit. This super Eddington feeding frenzy provides the first direct observational evidence of how black holes could grow so fast. They didn't just snack, they gorged themselves in brief, chaotic bursts, bypassing the theoretical speed limits we thought existed. The story doesn't end with light. It ends with ripples in space-time. The next frontier in this hunt is not a telescope, but a gravitational wave detector. Current detectors like LIGO can hear the chirps of small stellar black holes merging, but they cannot hear the deep, low-frequency rumble of supermassive black holes. Enter LISA, the Laser Interferometer Space Antenna, set to launch in the 2030s. LISA will be a trio of satellites millions of kilometers apart, firing lasers at each other to detect gravitational waves. LISA will be a tour's primary target will be the mergers of black holes in dwarf galaxies. When two dwarf galaxies merge, their central black holes will spiral together and collide. These events are too quiet for LIGO but perfect for LISA. Detecting these mergers will allow us to hear the population of intermediate mass black holes across the entire universe, even those that are completely dark and invisible to telescopes. We will finally be able to count the seeds. In conclusion, the discovery of massive black holes in dwarf galaxies is more than just a collection of anomalies. It is the recovery of the universe's lost history. Large galaxies are like reformatted hard drives. They have overwritten their pasts through violent mergers and unchecked growth. Dwarf galaxies are the backup drives. They have preserved the conditions of the early universe, keeping the secrets of how the first monsters were born. From the star-birthing jets of Hennes 2 to 10 to the silent, oversized heart of Leo I, these discoveries are telling us that the seeds of giants are everywhere. We just had to learn how to look in the shadows. As we peer deeper with Webb and listen closer with future gravity detectors, we are finding that the smallest galaxies have the biggest stories to tell. The monsters were never missing. They were just hidden in plain sight. Thanks for listening to G Fun Facts Online.